go.
Okay, so again, we're going to start talking about these different parts of our spherical mirror, and so then that way we can start doing something called ray diagramming. We did that last year. For ray diagrams, again, remember we're going to draw those 3 different lines, and they have to go through certain places on the mirror. Now, specifically, let's look at this mirror. I have this little line here, this line that goes right in between at the very half of that mirror. We're going to call this the optic axis. So the optic axis is just the axis, it's just a nice horizontal line that's going to go straight through the middle of the mirror. Okay, so optic axis, it's just a line that goes through the middle of the mirror. Our point C, our little C here, or I guess I should say capital C here, it's right in the middle. This is something called the center of curvature. Your center of curvature is the point on the optic axis that corresponds to the center of the sphere. Corresponds to the center of the sphere. So C just stands for center of curvature. And that is just the center of the sphere. Okay, your R, since this is a circle, your R is just a radius of curvature. So your capital R stands for the radius . Stands for the radius of curvature. And this is just the distance from the center of curvature, or we'll just call that C, because C just represents center of curvature. So your radius of curvature is just the distance from C to any point that's on this sphere at all. Okay, so R just stands for a radius of curvature, and we're going to talk a little bit more in depth about that in just a few more slides. There's one more thing that I also want to talk about, and that's the focal point. And we don't see that on this here, but we're going to see it in just a minute. So the focal point will be on in just a second. Okay, let's first let's talk about what happens when we use concave mirrors and what happens when we use convex mirrors. So a concave mirror focuses incoming parallel rays at the focal point. All the focal point is, we label that with a small f, a lowercase f. So a small f means focal point. I'm sorry, small f means focal length. A capitalized F means focal point. The focal point is just where all light rays converge. What do I mean when I say that light converges there? Jonathan, what do I mean when I say light converges? What does that mean?
It comes together at one point.
It comes together at one point. Very good. So in this case, I have a concave mirror here. How do I know it's concave? Because it's kind of like scooped in. I know it's like caved inward. So that would be like if we're like hunching in. So I've made a concave shape. So I know this is a concave mirror. I have light rays that are hitting this mirror. They bounce off. And if I follow this one, it hits this point. If I follow this incident ray, hits the mirror. If I follow the reflected, it hits this point. If I follow this ray, hits here, follow it back, it goes through this point. Every single one of these lines goes through this point. So that means this has to be the focal point because that's where all of the light rays are coming together. Okay, so where all of my light rays come together, that's the focal point. So in this case, this would be for a concave mirror. Now this one would be for a convex mirror. I have all these light rays that are getting ready to hit that mirror. And I see, as they hit this mirror, I can tell first of all that it's a convex because it's more shaped outward. So I know that this is convex. But if I follow these lines, this incident ray, it hits here, it bounces off this way. I have this one, it hits here, bounces back off this way. This one's going to hit and bounce right back in the same way. Hits here, bounces off. Hits here, bounces off. These light rays, if I look at this one, they all went through the same point. I don't see outside of that mirror that they've gone through a similar point. They're all diverging in different directions. If I'm following what's moving out here, they're all coming from different directions, so they're never going to intersect with one another. But I still see an image. So how is that possible? I see this image because it looks like light is diverging from this place right here. So we took that reflected ray, we traced it back to this point. We took this reflected ray, we trace it back to this point. This ray, we trace it back to this point. This ray, we trace it back to this point. So because we've traced it all back, we know that light should be, or it looks to appear, or it appears, it looks like it's emanating from this point. Even though it appears that way, it's not actually true. It just, our brains make it so that way it looks like it's true. So this would be a really good example of which type of image. What do you think, a real or a virtual? Virtual. And again, I have my C here, and all that C stands for is center of curvature. So I'm going to have a C. That just stands for center of curvature. I also have a C here, center of curvature. Now, we talked about the focal points. They're right there. One's right there. Now, the focal length we said was a lowercase f. I can see that here. Here's the center of my mirror. Here's my focal point. My focal length is just from the distance from the center of the mirror to the focal point. So that's true right here on this concave mirror. Let's look at this one. Here's my focal point for the convex mirror. Here's my center of the mirror. That means that this must be my focal length. So the distance from here to here, that's my focal length. Distance from here to here, that's my focal length. Okay, so concave mirrors. Are we good? Tell me when you're ready.
How do I stop it? How do you stop it?
Make sure your hand isn't touching any of it. Press done for the low battery.